lose spin. Again, you can reflect on that, from the book or from the YouTube video or whatever. But you lose spin by spreading out. The air loses that spin so that it can make the straightaway by spreading out, by having upper level divergence. So out ahead of the trough, but not as far as the ridge, east of the trough, west of the ridge, hopefully you got that question right in the quiz today, is an area of upper level divergence. Now, if you think about what that means down at the surface, though, down at the surface, pressure is just the weight of the air above you. If they're having upper level divergence, air is spreading out. There's less air than there was before. So there's less weight than there was before, and the air weighs less, and the pressure goes down at the surface. We have created a cyclone. We have experienced cyclogenesis. Hooray, we've given birth to a happy baby, nascent little cyclone. Now he can go through his whole life cycle. He can be an open wave, and then he can become an occluded cyclone, and he'll always eventually become an occluded cyclone. Once he becomes an occluded cyclone, though, things change fast. Because their temperature is pretty much the same on both sides of the occluded front. It's cold on both sides. The warm air mass, there's still a warm sector. It's just way away from the cyclone itself. See how there's a warm sector down here? There's still a big temperature difference between this side of the cold front and this side, or this side of the warm front and this one. But there's no temperature gradient anymore. There's no temperature difference across the occluded front. And so there's no reason by the thermal wind relationship for there to be a jet stream there anymore. No jet stream means no positive vorticity advection. No positive vorticity advection means no divergence. No divergence means there's no reason for the pressure to be low anymore. And with time, the pressure will start going back towards normal. The cyclone is experiencing cyclolysis, the death of a cyclone. Now, which I think, this is a horrible picture. We don't want that one. It just makes things harder. It's a good idea at this point to show some examples. Now, in the PowerPoint presentation, we walked through a couple of examples of how there was a trough. We made a map of the vorticity, and it was positive where it should have been. And then we made a map of the advection, and we saw that the advection, positive vorticity advection, was large where it should be, out east of the trough. And then we made a map that showed where the pressure was at the surface, and the pressure was low underneath there, and it all worked the way it should. So this is a typical way to explain these sort of things. And I happen to have a particular storm in mind, but the problem is, it's not one of these damn plots where this projector has problems with black and red. So I'm going to do my best to show you this guy, because he's, let's let it be dark for now. All right. This is the March 1993 storm of the century. Oh my goodness, the storm of the century, or the so-called superstorm, really was something that we have never seen before. It happened to be occurring, I was in grad school at the time, and I was in grad school in Indiana, and it was spring break, and my friends and I went to Washington, D.C. Woohoo, spring break Smithsonian. I forget why we went to D.C. There was something going on, a concert or something, I don't remember. Anyway, we went to Washington, D.C. And being good little meteorologists that we were, we found out that they were expecting this enormous storm. And by storm, I mean cyclone. Now, one of the strange things about that even meteorologists have a hard time explaining really is the fact that really, really extreme weather events tend to be very well forecasted. And even like a week in advance, they were saying there is going to be one hell of a cyclone over the East Coast. And of course we went anyway. I forget what day of the week the 13th was. There was this huge trough in the jet stream. Now, I know that you haven't seen a lot of troughs. And that the troughs that we've seen have mostly been things that I just drew. When I draw a trough, I tend to draw something that looks like this. Where here's a trough and here's a ridge. But, if you get real weather maps out, a much more normal pattern would be, like there's a trough and there's a ridge. They're not really they don't have a very high amplitude, okay? It's just that that's not so, it's clearer that this was headed to the south and then turned to the north. So I tend to draw them in kind of an exaggerated way, and so does your textbook. But, holy crap, That is a trough. You see this trough here? The winds are geostrophic at these levels, so the winds are flowing from the north, and then they make this crazy sharp turn down here over the Gulf of Mexico, and then head back up north along the east coast. That is a trough, the likes of which even God has never seen. Okay, that is a trough that when the computer models made the forecast for it, they said that can't be right. We can't have a storm that big, a trough that big. Well, they did. That is one giant trough. I have never seen one before or since, and frankly, neither had anybody else. That is a big trough. So right down here at the base of the trough, one can imagine that there was a heck of a lot of vorticity, right? Air is shooting down this jet stream, heading down towards here. It's geostrophic flow. It's got to make this turn. That is the winds in the storm of the century are like 250 miles an hour a lot. These winds are really shooting along. They got to make a big sharp turn here. There's a lot of vorticity going on here. On the other hand, out here over the east coast of the United States, the flow is pretty much straight. It's parallel to these isobars, so it's just going to flow straight. So there's a whole lot of positive vorticity advection going on. Again, the kind of positive vorticity advection that even God had never seen before. Sorry for the sacrilege, but it explains. Okay. I don't remember what all pictures I happen to have up here. Okay, so if out here ahead of the storm, we have so much positive vorticity advection, then apparently there's a whole lot of if we got to lose a lot of vorticity, if we have to lose all the vorticity that it took to make this little curve, we got to really have a whole lot of spreading out, a lot of divergence, which means down at the surface underneath this, we're going to have really, really low pressure. How low, you say? Well, here's a map of the pressure at that time. Here's the isobars of pressure. They're ugly, by the way, because there was a data problem. I mean, whatever. Anyway, so here is our isobars. And let's see, so for example, over Omaha at this time, it's about 1,027 millibars, about 1,020 over Illinois, about 1,004, oh my God, 1,096, 96, 998. If you go all the way down here, 966 millibars at that time was the low right over DC. You know what else has a pressure of like 966 millibars? A hurricane. Okay? This is about the deepest damn mid-latitude cyclone anybody's ever seen. Okay? Normal pressure is about 1,013 millibars. A typical low-pressure system that would come through any old given day in Omaha, maybe 1,005 millibars, whatever. Holy crap! This is like a hurricane of snow. This should not be happening. This has never been seen before. But it makes perfectly good sense, right? There's all this positive vorticity advection going on. So above the ground, there's all this divergence, which makes the pressure just get lower and lower and lower. This is a type of storm, by the way, that's a nice example of what is called a nor'easter. We're going to learn about nor'easters in the 5th unit of the course, but just so that you've seen that word, this is a nor'easter. It's a big wet snowstorm in the east coast. But a typical nor'easter has pressure like 1,000 millibars. 966 millibars? My God. Should not be. Should not be. As this thing approached, you can well imagine the media was freaking out, right? This should not be happening. This is going to wipe out. We're going to be buried in snow, whatever. Part of the reason why we were going is because my friend from college was going to be starting out on the Appalachian Trail, which is a hiking trail from someplace in Georgia to someplace in Maine. Yeah, so we were like there to say goodbye, because you have to start in like March if you're going to make it. Yeah. Where he was going to start, which was someplace in northern Georgia, they got over 4 feet of snow. Feet in Georgia. So this thing's coming up towards D.C., and we're like, we got to get the hell out of here. And so we went up to what was then National Airport, now it's Reagan Airport, and of course everybody else in D.C. wants out too, right? And we get to the front of the line, and the person behind me in line is one of my professors at Purdue. And he was there for some conference or something. Nothing redeeming, whereas I was just there to, hang out, whatever. And I said, put me on a plane, I don't care where, out, away from the storm. And I ended up in Minneapolis, of all places, which was near the center of the high. Nothing going on. It was beautiful for the rest of spring break in Minneapolis. But my poor professor did not get out and spent like 4 days sleeping on a bench in an airport. And not very happy with me, but whatever. This is an amazing storm. Oh, by the way, here's the animation of him. So here's the area of low pressure forming. See, it's a terrible animation, but whatever.